F.2, Introduction to Mergesort. In this part, so we will learn a new sorting algorithm, Mergesort. Yeah. So you may ask this question, why we need to learn a new sort, right? Yeah, we have learned selection sort, bubble sort, and insertion sort, right? Why these sorting algorithms are still not good enough? Yeah. I'd like you to think about the worst case of these three sorting algorithms, the worst case. Yeah. Just to recall a little bit, worst case efficiency, right, of these three. So you can see, yeah, big theta of n squared. For all three, big theta of n squared. So that's not very good. Yeah. We want to have a sorting algorithm whose worst case better than that. Or we want to improve the worst case to big theta of n log n. How about that? N log n. Yeah. So if we can do that, then in some situations, if we want to control the worst case, so we can use this new sorting algorithm. Yeah. So that is the motivation to solve this problem. Yeah. All right. So keep that in mind. So we try to find a new sorting algorithm to achieve this goal. Yeah. All right. So let's start. Yeah. First, let's look at the problem. The problem number 16. Merge two sorted arrays. Here you can see still it's not a sorting problem directly, but it is some problem related to the sorting algorithm. Yeah. All right, so let's look at the problem. Given two ordered arrays, already ordered, yeah, how to merge them to get an ordered array? How do you use the minimum number of comparisons to merge these two ordered arrays to get a new ordered array? So that's the problem. Later you will see if we can solve this problem, then another sorting algorithm is almost there, very close. Halfway there. Yeah. All right. But now I need to explain why we need to solve this problem first. Yeah. So I need to give you the background, yeah, or the motivation for this problem. Yeah. So let's look at this, the motivation. Yeah. Here, let me describe a story. Okay. In order to, let you see a good reason to solve this problem. So I want to describe one special story. So this story is, we start with this question. How to sort a huge array. So think about this. This time, we want to sort a huge array. Okay. So you can imagine the array size is extremely big. Okay. So when you have that, so you think about the data size so big, how do you sort it? Okay, how do you sort it? Yeah. Right? Yeah. The number. So you can imagine. Let me even say in this way. You cannot load all your data into the main memory. You do not have enough main memory to hold the data. Okay? Yeah. So that's why if you use the regular sorting algorithm, there could be some problem. Okay? Yeah. Or let me just give you a little more background information. The data, the large part of data has to be stored on hard disk, on your hard drive. You can only, every time you can only load a portion of data into the main memory. Okay? Only portion of. How do you sort it? Okay? Yeah. Imagine that. Yeah. All right. So now, here, I like to describe some idea. Yeah. All right. The title of this module, Divide and Conquer. Yeah. Can we just use the divide and conquer? Yeah. No. So it's naturally using that divide and conquer idea. So here, because that size is so big, we want to divide it into subarrays. Okay. All right. So let me just use this diagram to describe. We divide into these subarrays. Smaller subarrays. For smaller subarrays, we can apply regular sorting algorithm, right? Much smaller. Yeah. In this case, we can apply our usual sorting algorithm easily. Yeah. Okay. When we apply subarray by subarray, okay, subarray by subarray, yeah, we can get each subarray sorted. Okay. Then the next step, how can we make the whole array sorted? So when you want to do that whole array sorted, now you need to solve this problem. Merge two sorted arrays. Okay, so look at here. If we can merge two sorted arrays, the first two, we merge them. The next two, merge them to get a new ordered array. Yeah. The next round, merge these two sorted, right? Yeah, things like that. So in that way, we may need a solution, a good solution for this problem. Okay, all right. So that's the background story. Yeah. All right. So another possibility, yeah, because this array is so huge, sometimes people can consider using parallel computing, right? So multiprocessors, parallel computing, each processor you can assign one array to that processor to be sorted, right? Yeah. Okay. Yeah. After that, so then you merge. So how about that? That idea, right? Parallel computing idea. Yeah. So anyway, yeah. So now, so I hope you can see there is a good reason we should solve this problem number 16 first. Yeah. So let's do it. Yeah. All right. Next, let's consider how to merge two sorted arrays. So what is the best way to merge two sorted arrays? Yeah. All right. Okay, yeah. So the situation, so we have seen it. Yeah. Now, regarding the solution, yeah, the strategy, new strategy. Okay, yeah. The strategy here is, or the idea to get started, take advantage of the structured data. each sorted array, it's a structured data, right? Yeah. That order, yeah. That is the good property. We want to take advantage of it. Yeah. So that's the, general strategy. Right? But still too general, we need to have a little more specific implementation ideas. Yeah. All right. So let us look at the existing sorting algorithms we already have. So we want to borrow some useful ideas from existing sorting algorithms. Yeah. Because we have that experience. Experience is valuable in problem solving. Yeah. So we need that. Yeah. So let's take a look. Yeah. But when we select from those existing sorting algorithms, we do not want to use those that do not take advantage of the order information. If a sorting algorithm does not use the sorting information, order information, that is not very useful for our purpose. Okay, all right. So with that in our mind, so let us do screening on our existing sorting algorithms. The first one, selection sort. Think about, for the selection sort, do we make use of the order information in selection sort? No. In other words, if the array is already sorted, is your algorithm running faster, right? Faster? Already sorted. If your algorithm is not doing faster, that means it does not take advantage of the order information. So you can see for the selection sort, no. Even already sorted, you still need to use n squared, big theta of n squared. That kind of efficiency. So the answer, it does not use order information. All right. So selection sort gone. We cannot use it. Okay. The second one, bubble sort. Bubble sort. If the array already sorted, already ordered, yeah, in increasing order, can we run this algorithm faster? No. Still you do bubble, right? Still do bubble, right? Same efficiency, same performance. So it does not use the order information. Right. Next, insertion sort. Insertion sort. If the array already sorted, ordered array, can we run our algorithm faster? Answer is yes. Yeah. Because if it's already sorted, that corresponds to the best case, right? That corresponds to the best case. And what is the efficiency for the best case of the insertion sort? Big theta of n, right? N. That's the one. That one is useful for our current problem. Okay? So we select it. That means this one is a good candidate we should use. Yeah. We want we want to build our new sorting algorithm on top of this insertion sort. Borrow some of the, useful things from insertion sort. All right, yeah. So here you can see, we need to build new solutions on top of our old experience. Here, it's a good example. All right, but here, to enhance our confidence. So I want to point out one thing. Recall, insertion sort is good for almost sorted array. Remember? Yeah. In our discussion after the insertion sort, I mentioned if an array is already almost sorted, only there are scattered places, a few scattered places, clusters, that portion, the data not ordered. Other than that, the whole other places all sorted. For that situation, insertion sort is a good solution. Here you can see this property tells us insertion sort really takes advantage of the order information. All right, so let's move to next step. We want to get a better understanding, to build up solution for this problem number 16. All right, so let's start. Here, when we start, we want to look at our insertion step first, and try to connect this insertion step to our new problem number 16, and see how do we, try to use it to inspire some new idea. Okay, all right, Why we take a different view, so in problem solving, I mentioned a few times before, sometimes we need to take different views on the same problem. If we can take a new view, then we may get a new solution, or we may improve our old solution. All right, so that's the reason. All right, so here we want to get some new idea. All right, so let me describe the general insertion step. We want to insert this V into an already sorted array. Okay, the detail, I do not need to go through the detail. Okay, we already know the answer, the solution, so we do not need to look at the insertion detail. All right, but here I want to connect to our current problem number 16. To connect to it, can we treat this one element array as another sorted array? One element, already sorted. It's a special case. Yes. So here, we need to adapt our view to this new interpretation. This one element array already sorted. Here you can see this insertion step becomes a merge step. Merge two sorted arrays. How about that? This new view, we do not have this kind of view before, so this is a new view. Okay, all right. So this new view, probably it can help us to find a solution for problem number 16. All right. So two sorted arrays are combined to get a new sorted array. Although it's a special case, right? One of the arrays has only one element, but can we generalize it, right? Yeah, one element. So we try to, extend our idea from one element to multiple elements. Can we do that, right? Yeah. So here, based on this new view, so the insertion step, we change the view on the insertion step to take the merge view. Merge two sorted arrays for a new sorted array. Insertion view, merge view. From insertion view to merge view. Okay? All right. So now, this merge, so here you can see only one word change from insertion word to the merge word. One word change. But the idea also changes. So we have a new idea, new view, new idea. Yeah. All right. So let's apply this new view on our problem. Okay. Yeah. When we apply the new view for the insertion step, we merge two arrays. One array has size k, another array has size 1. K and 1 merge. Yeah. But when we do that, we notice these two arrays, our data is not quite balanced. It's not balanced. Okay? K and 1. The data size difference is big, not quite balanced. Yeah. And based on our experience, we know if our data is not distributed evenly in a balanced way, usually the performance will not be good. Yeah. Okay? Yeah. So this kind of unbalanced data distribution may cause poor worst case. Yeah. The worst case will not be good. Yeah. So that is a problem. Yeah. All right. So how do we improve performance for the worst case? We don't like a very bad worst case. Remember at the beginning, when I talk about the motivation, the reason we want to have a new algorithm, so we want to make the worst case big theta of n log n, right? That means we want to make the worst case efficiency better. But this unbalanced phenomenon will give us problem to do that. So we need to change that unbalanced data arrangement. So for that reason, we need to do some change. Okay? Yeah. Here we also get back to the balancing principle. So remember we talked about the balancing principle before. Right? Yeah. So here, the balancing principle tells us when we have option to choose to split our data, we want to make the most balanced way to split the data. Then the worst case will not be very bad, so we can control the worst case, not to be too bad. Yeah. So that's the balancing principle. Yeah. Try to make two subarrays of equal size. As close each other as possible. Okay? So if we have option to do that, we will make that happen. Yeah. All right, so based on this analysis, all right, yeah. based on this analysis, we will solve the problem number 16, but in the next video. So not this one, the next video. All right, so let me stop here.